Hello students, in this video we'll discuss the discrete Fourier transform. Let's consider the space L2 of Zn just as the set of all complex n-dimensional vectors such that the Zj are in C for j between 0 and n minus 1. And with the additional catch that I can define zk for any integer k if it's equivalent to one of the things mod n, right? So in other words, what we can say is we can define this by periodicity mod n, right? So we can extend mod n. Okay, good. All right. And so in particular, what this would say is if j is in this range, then we could say that zj plus k times n for any k times n is going to be the same thing as zj. So if I shift by any multiple of n, I get the same thing as zj if j is in the same equivalence class mod n. Okay, great. So that's the sort of the periodicity assumption of these sequences. And now this is an inner product space. So the inner product on this space is I take two sequences. I do the inner product of z and w. And I just do the standard inner product on Cn, right? J goes from 0 to n minus 1 of Zj, and then Wj complex conjugate, okay? And so what I'd like to do is I'd like to find an orthonormal basis for this set. And so what I'm going to do now is I'm going to consider, so let zeta be e to the 2 pi I over n, be a primitive nth root of unity, be a primitive nth root of unity. Okay, and I'm going to define some functions that reside in this space over here. So define phi k. How I define this? I'll define phi k at L is going to be zeta to the kl times a normalizing factor 1 over the square root of n over here. And so here this is defined for L equals 0, 1, all the way up to n minus 1. So that's my phi k, right? So I have a sequence, and I claim that the sequence phi k, claim this family, phi 0, phi 1, phi n minus 1 is an orthonormal set, is orthonormal. In L2 of Zn, okay? And of course, that just follows from the fact that these are roots of unity and they follow a cyclotomic relationship, right? So let's do the calculation over here. So let's do the inner product, say for example, of phi k and phi k tilde. What would that be? That would just be the sum. Let's say j goes from 0 to n minus 1. They each have a 1 over square root of n, so that's going to be a 1 over n. And then we'll have a what? We'll have a zeta to the power k minus k tilde times j, of course, times j. And of course, one thing happens if k is equal to k tilde, then all those are 1, and I have exactly n1. So we see that this is going to be equal to 1 if k is equal to k tilde. If k is equal to k tilde, beautiful. And then if k is not equal to k tilde, that's going to be a root of unity, and this is just a cyclotomic polynomial, right? So in other words, what we have over here is we have a root of unity plugged into a cyclotomic polynomial, right? A root of unity plugged into a cyclotomic polynomial is 0 if k is not equal to k tilde, right? We proved that in a previous video, right? Okay, excellent. So this is an orthonormal set. And so now what I want to do is I want to use the fact that I can expand any function in an orthonormal set. So what does that allow me to do? That allows me to write any z as what? As the sum for any L2 function on Zn, any L2 vector. As the sum, j goes from 0 to n minus 1 of z with phi j, okay? And so what are these coefficients over here? These coefficients over here, well, let's write out what those things are going to be. So these z with phi j is going to be the sum. Let's say k goes from 0 to n minus 1 of just what? Of just zk times 1 over the square root of n. and then times this complex conjugate of this thing over here. So that's going to be zeta to the k to the negative k and then L. Because I know that zeta, so we're using here the fact that zeta to the negative 1 is the same as zeta complex conjugate because it's unimodular, right? Okay, and so what we're going to have over here is now we're going to set, I'm going to forget about this 1 over n, we're going to define, so here's our discrete Fourier transform, so it's just up to a normalization, the same thing. So now define z hat of k, z hat of L. What will z hat of L be? Z hat of L is going to be this thing over here. It's going to be the sum. K goes from 0 up to n minus 1 of what? Of zk. Of zk. Then zeta to the k. Zeta to negative kl. Negative kl, like that. And so this vector over here, so of course if I want to write this in terms of just the exponentials, this would be the sum. K goes from 0 to n minus 1 of zk, and then e to the minus 2 pi I k L over n, like so. And so if we write down this vector over here, this vector is z hat of 0, z hat of 1, z hat of n minus 1, this whole vector over here is also in L2 space, and this is the discrete Fourier transform. So this is the discrete Fourier transform of z, discrete Fourier transform. So in other words, this discrete Fourier transform, I have a way of mapping L2 of z into L2 of zn into L2 of zn by this mapping over here. So I can take this vector z and map it onto this vector z hat, and that's the discrete Fourier transform. In further videos, we'll see how the Plancherel theorem, how the Parseval theorem, how the Fourier inversion works. But this right over here, we can sort of see there's a linear structure to this too. So I can actually find out, and we'll see in further videos, how I can represent this Fourier transform, the discrete Fourier transform, as a matrix applied to the original vector z. And we'll study the invertibility properties of that matrix and the spectral properties of that matrix as well. Thank you very much.